welcome everyone to this webinar on sustainable aviation fuel. So as I think everyone understand nowadays, we are in a very challenging world that we want to talk about decarbonization and sustainability. And that is why we are coming into this webinar so that, we can join up people from academics background, from market, from industry, so that we'll have an insight into what to do and how the industry can help in countering the issue. Okay, so first of all, before I proceed, I forget to introduce myself. I'm Dr. Chin from Department of Chemical Engineering, Universiti Teknologi PETRONAS. Okay, so before we proceed further, can I invite our Dean of Engineering, Prof. Tang, to give one or two welcome speech to all the attendants. Okay, thank you.
Okay, good afternoon. Thanks, Dr. Chin.
So Prof. Tang, to you.
Okay. Good afternoon. I'm the Dean for Faculty of Engineering. So I'm proud to see our academic committee come together with leaders from the industry to explore one of the most pressing challenges and opportunities of our time, decarbonizing aviation. Aviation has been a long symbol of human ingenuity, connecting continents, cultures, and economics. But as we soar higher, so too must our responsibility to the planet. Sustainable Aviation Fuel, or SAF, represents not just a technical advancement, but a paradigm shift towards cleaner skies, circular economics, and resilient energy systems. SAF is a great challenge across the refinery industry and across aerospace industry. Process is being made to allow SAF to be used as 100% replacement to petroleum jet fuel on aircraft. On December 1st, 2021, United Airlines made aviation history by flying the first passengers flight powered 100% by SAF, taking passengers from Chicago airports to Washington's National Airport. So SAF can reduce greenhouse gases emissions by up to 80% on life cycles emissions basis. Today, we are honored to host 3 exceptional speakers whose work spans the frontiers of research and industry applications. Their insights will help us understand the science behind SAF, the hurdles we must overcome, and the collaborative spirits required to make sustainable flight a reality. So let this be sessions to be more than just a seminar. Let it be a launch pad for ideas, for partnerships, and for the next generation of engineers who will carry this mission forward. So thank you for being here. Let's begin. Thank you, Dr. Chin.
Okay, so thanks for your welcoming speech, Prof. Tang. Next, let's start the webinar. Okay, so before we start, I would like to remind everyone, including the speakers, that this session will be recorded, and then after that, we'll put it onto the online platform so that any audience that can't make it today or things like this, they can follow up and listen to our webinars. Okay, right. So first of all, before we let's start our first speaker. Let's invite our first speaker, Prof. Shanyan, to give a talk into his work. So just very quickly, Prof. Muhammad Prokashnian, OBE, holds the chair in energy engineering in University of Sheffield, and then he's now leading the Energy Innovation Center. Okay, so just very quickly that he's also a General Secretary of IFRF and the Managing Director of both TRC and SFIC. Okay, so he has more than 500 peer-reviewed publications and leaderships in more than 100 of major research projects. Expertise in CCUS, computational modeling, and SF model development. Okay, so without further delay, so Prof. Kashnin, so this is your time now, okay, for 15 minutes. Thank you.
Please unmute yourself, Professor Mohammed. Unmute yourself.
Yeah.
Good morning and good afternoon to everyone in the webinar. And what I will try to do in the next 15 minutes, provide a very brief presentation, very quick presentation, and hopefully initiate some discussion. So I go through to the presentation setup. Can you see my presentation?
Yes, sir.
Yes. Yeah, okay, excellent. So I go for full. Sorry. Okay. So what I will try to do in this presentation, first of all, to say why UK is at this moment has a strategy and a planning for introducing SAF at a national level, as well as taking a lead in terms of SAF production in future at international level. So what we do at EIC, all the way from fundamental research, lab-based research, to the pilot scale research, and all the way to the refineries. So these are the sort of research activity we do at University of Sheffield. Sheffield University is one of the Russell Group universities in UK, and it has a significant development and research activities in the area of not only on the aviation, but materials and other area of aligned with industrial need. So very briefly to talk about why SAF is important. I'm sure you all know about the UK SAF mandate, which is more or less driving the decarbonization in aviation. And more importantly, attached to that mandate, we also have the revenue certainty mechanisms, or what we call RCM, to make sure that industry and investors have trust in the strategy and therefore to attract private investment into the country. Overall, the aim is that by 2030, 10% of the all fuel used in UK should be SAF, and that is already started from 2025. 2% is the target, 10% by 2030, and by 2040 it will go to around 22-24%. Of the certain amount of that has to come from the power to liquid. Aviation currently accounts for approximately 7% of the UK carbon emission, but what is important is the rapid growth in terms of the emission level generated from this sector. And the mandate mechanisms serves a number of purposes, reducing emissions from the aviation sector. That is one of the aim, creating opportunities for domestic SAF production in UK and establishing UK as a leadership in sustainable flight. So what the government does in terms of SAF production and encouraging investments, in July 2022, we had advanced fuel funding of approximately 135 million. That followed by AAF3, which is a short period of time to where 63 million pounds more is available for the funding. And now these projects are really to encourage production of SAF in UK using a novel technology. We are receiving one of these funding, and I will mention that in next slides to see how it's been done. But let me talk about EIC and what is Energy Innovation Centre. Energy Innovation Centre is set up to provide bridge between the academics and industry. Total funding comes from the government, UK government, as well as EU. And the funding is in the past 3 years has been around just under 40 million pounds to set up the facilities. More importantly, we are aligned ourselves not only with UK government policy, but also with industrial need. And that is why we have Boeing as our founding members, followed by Airbus, Drax, and Rolls-Royce. They become as a part of our industrial members that fund our activity. In addition to that, we provide platform for testing and scaling. And we also act as a collaboration hub between at the national and international level to create that link between industry, academics, and the partnership. In addition to that, 2 years ago, we were selected by UK government, Department of Transport, to be the UK SAF clearinghouse. So this is the second SAF clearinghouse operating. Of course, the European Union is also just initiated a new one. That will be the third, but ours was second after the US clearinghouse. Now we are supporting industry and fuel producers to certify their fuel and make it available for industry. But what is the Energy Innovation Center focused on? Rather than showing this diagram in order to meet my 15 minutes, let me tell you what we try to do in our end. The pictures and photos you see there is part of our activity and our facilities. We have bioenergy facilities that includes waste to energy, biomass. We also have a gasifier, wooden gasifier. These are in a pilot scale level. Biogas turbine, a turbine that works with biogas or with hydrogen. We also have an engine, marine engine that operates with bioenergy, as well as, of course, combustion test facilities operating with hydrogen or normal fuel and even biogas. In addition to that, we have carbon capture technologies involved, and that is a next generation technology like a molten carbonate fuel cell and amine capture plant and rotating packed bed, as well as the direct air capture. Overall, we capture around 2.5 tons per day of the CO2 when few of these items work together. Plus, we also produce hydrogen from electrolyzer. And as you can see, we have all the components for the SAF production. And that is the SAF produced from the CO2 and hydrogen, or from syngas and hydrogen, and that we have a Fischer-Tropsch pilot plant, which produces around 200 liters a day. Then fuel that produced from that goes into the fuel analysis lab, part of our contribution to the UK SAF clearinghouse. And we do have an aircraft engine, APU engine, where we test the performance of these fuels. This is our next generation technology that have received funding. It reduces the cost of hydrogen, the SAF production by around 40% using this technology. And we will provide more information on this if there are any questions available on that. Our work with industry, we work very closely with industry. We did all the tests for the Flight 100. You may know about this flight. This took from London to New York down in 2023, November 2023. And we used 100% SAF in both engine and looked at the performance of the engine. And some of the results that obtained from that result shown in here. We tested that fuel in our lab using the laser diagnostic facilities. And what is interesting to see, these are the output from on the left-hand side of the picture, the output of the particulate emissions. And if you look at the bottom section of the jet fuel system, you can see that emissions generated from the conventional aviation fuel, when we introduced SAF, you can see a significant drop, around 70% by mass or 40% by particle number density, significant reduction when SAF was introduced.
Prof. Shanian, you have
Yes.
5 minutes left. Okay.
Sure.
Okay.
Challenges and opportunities, therefore, ahead is the scale-up challenges is a major issue that we are looking at, how to meet that 10% mandate. It is very important if you look at the numbers of the SAF production at this point in time, if we are only producing about 0.3% to even close to 1%, and even in the more optimistic level, 3% at certain countries, in certain airlines. But to meet the 10% is a challenge. Rules and regulation, approval process, technical standards, certifications remains time-consuming and costly barriers for these fuel producers. And UK advantages is that we already started doing this work, not only on the fundamental level, but also on a pilot scale level. And therefore, looking at the aviation as an international challenge, decarbonization of aviation is an international challenge. Therefore, collaborative activity will become very important. And finally, with my final slide to say that we are continuing investment in SAF research and development and commercialization. This remains essential for us to meet the 2050 net zero commitment for aviation. Altogether, Sheffield EIC Energy Innovation Centre, that includes Turk and SAF IC, we do all our work in a way to align our activity with the UK government policy, but also encouraging international collaboration. Advanced fuel funding that available from UK provides that opportunity to work with others and try to bring in more collaborative work in this challenging sector. And finally, together at the national and international level, we can lead that global green aviation revolution and transform how the world flies and move it to a very green future. And that's my last slide. Thank you.
Okay, thank you, Prof. Shanian. Do you have 1 or 2 more of your opinion to add in, since we still have 2 minutes? Just very quickly. Okay, is okay. So in that case, thanks, Prof. Shanian, for your giving us insight into how UK government is invested in this, what do we call, invested in this SAF research. Okay, so next we going into our second speaker of the webinar, so Prof. Tala. Okay, now, so Prof. Tala is Executive Dean of Higher Education and at Aviation Australia, Queensland government. And then at the same time, he's also a professor at the Central Queensland University. And what Prof. Tala will talk about today is actually hydrogen for aviation. Okay, so Prof. Tala, let me pass it to you now. Okay, thank you. Thanks.
Thank you very much, colleagues, and thank you for UTP. Can you see my screen? I'm sharing screen or not?
Yes, we can see your screen.
Okay. Thank you very much again. Look, I don't want to repeat what my previous colleague said, and in this 15 minutes, I want to tell you, like, I work for Aviation Australia, and Aviation Australia is not a university, but not industry, but industry. So we are having a little bit of everything. And we're the glue between the R&D, between the industry. We work with Airbus and Boeing, and we are also very close to regulator. And our bread and butter is we graduate aviation maintenance engineers. We have nice project to share with colleagues here, and this project is on hydrogen for aviation industry. Again, to me, hydrogen is the most ideal alternative fuel for aviation, beside SAF, of course. And the reason, because that will contribute to reduce the emission significantly. As we all know, H2 plus O2 will give you H2O. Temperature is increasing and we need solutions, of course. And I just wanted to share with you also the G1, 2, 3, 4 of the industry of aviation and where we're at now with aviation 4.0. And I've done work for my government about aviation 4.0 and where we're at using the technology. Sustainable fuel and sustainable aviation or SAF fuel, it got plus and minus, as everyone knows. And I just quote here some of my PhD student statement, like, okay, we're solving the problem, but we still produce a little bit of oxide of nitrogen and CO and CO2 and so on and so forth. So with liquid fuel, I think we still produce a little bit of exhaust gas emission that need to be addressed. And because of that, I have a very young, strong team who are not academic at all, and they're all engineers and pilots. They come and they've spoken to me, and I give them hangar and one aircraft, and they start converting this aircraft to use hydrogen. We're halfway. What are the challenges of using hydrogen? In summary, the cost is still very high. Safety is a problem, and infrastructure is another big reason. And there's a limitation of current device to use hydrogen. Again, fuel cell, or I think UCL, they're burning hydrogen in gas turbine. And finally, government regulation and policy. So if I combine these together, we all need to work together, as mentioned previously, to tackle this problem and complement each other. The question is hydrogen safe or not? Again, everything not safe when we started, but it becomes safe when it's up and running. And that's why I feel hydrogen is safe. But we need to convince the regulator, we need to convince EASA and CASA and CAA of Malaysia to tell them it is safe. Many reasons. I don't want to go through the technicality. Where we're at Aviation Australia, and Australia in general, we use alternative or renewable energy resources for airport. We have few buses operate on hydrogen. And also we are now producing green hydrogen. And by the way, I'm sure you know Australia produce a lot of brown hydrogen from coal and gray hydrogen from methane. But now I'm talking about the green hydrogen. That's why it is expensive. So for airport, we started working with Brisbane Airport, and we have a very strong link with them. Actually, our office based on Brisbane Airport. And what we're doing, I like this slide, and this slide shows that if we wanted to change one of the units of the airport, how long do we need, how much we need, and when we're going to get return of investment, and what is the effect on environmental pollution. Example, Adelaide Airport is now almost, they do a lot of decarbonization, but almost reaching the level where they reduce the emission dramatically. Another area where Aviation Australia, we are about 25% of our business located in drone and drone technology. We train student and defense, and I think this year we done, not me, Ryan, about 1,500 students, and we're certified by, we're licensed of Queensland government, so we sign on behalf of the government. We have about 5,500 students in Saudi as well, and in Malaysia we have also a very strong link. So again, since the drone is part of our business, Ryan and I, we decided to play with one drone and say, how if we convert this drone into hydrogen? And as you can see, the blue color is the fuel cell, and it gives you a lot of endurance and also payload. So we demonstrate this to school students and universities. Some technical information about the drone is available here. What is the source of green hydrogen, or what are the technology? The technology is electrolyzer, very basic, and I've just had some discussion before this webinar, and I've been asked question about whether we are going to produce a green hydrogen, and the answer, we can buy electrolyzer from a well-advanced country who are specialized in this, such as Japan, Germany, etc., instead of wasting our time. So integration is the goal. I want to show you also, this is the Gladstone. It is the largest port in, maybe one of the largest on Earth, but in Australia, definitely it is one of the largest, and the largest maybe. And we're selling LNG and CNG to Japan, South Korea, and Taiwan. And now we're working CQ, my university, Central Queensland, with the investor who's Andrew Forrest. He's a multi-millionaire, to pump 30% of the gas to be hydrogen. And again, this is something is happening in CQU. I think the recommendation for hydrogen, we need to think of long term. We need to do a little bit of commercial, which is again something we are doing now. The risk of first mover, support R&D, and many other things. But in general, I think we really need to build awareness, and we need the government support, which is happening so far in Australia. Of course, developing the technology, and we need to also graduate technologists who can deal with the technology. The cost is low, and it must be. I mean, the cost is high. We need to make it low. And here is the Australia cost of green hydrogen. Well, we are now converting one aircraft to they call Beach 1502's hydrogen as a fuel. We remove the gas turbine, and now we're doing a fuel cell, and it is happening. And I will show you some of the photo at the last slide of this presentation. We talk about challenges. This is my organization, and as I said, 4,000. We graduate many maintenance engineer. We're part of CASA and EASA. We got about a dozen of aircraft, so we are very handy when it comes to aircraft, and we do a lot of certificate, and sometimes it's important to think of certificates, and one of those short courses is hydrogen and hydrogen safety. The very last bit of this presentation is Strala. Strala is a company, a commercial company led by Bob. Bob, he came to me like 3-4 years ago, and we start discussing, can we or can't, convert this aircraft to use hydrogen, and I was very supportive. We give him a hangar and a small jet, and they start playing with aircraft, and they start making a lot of collecting donation, and now we are, or they are actually more than 50 staff members. So they start for now 50, and now we have aircraft already operate on hydrogen, not yet flying. So hopefully in 2026 we'll start the first trip from Brisbane to Gladstone, which is about 400 kilometers. Now they are very commercial, as I said, and that's why they wanted to produce the first aircraft by 2032, and it will be on market. And that's why, yep.
Prof. Talat, 9 minutes.
Sorry? Sure.
9 minutes. Yeah,
Yep.
but I think we still have time. Don't finish earlier.
Yeah,
Okay.
I'm trying to
Thank you.
finish earlier, but anyway.
Yeah.
So, well, in this case, I just wanted to talk about a drone, if I have some time, because drone is another emerging technology device, and we really doing a lot of work in drone, RPS. Ryan, he always traveled to Vietnam, Malaysia last time, and Indonesia, and recently in Dubai and Saudi. And what we're doing actually, we're using this drone technology, but we realize we need longer durability, we need zero emission, and we need higher payload. And that's why we start thinking seriously of converting this drone into hydrogen. And also this will definitely contribute to build awareness of our kids, our students. For CQ and Aviation Australia, we partner together and we start developing what I called it when I present this to the government. I said, now we graduate many technician who can change the nozzle and jet and tire and all these things, and we call them B1, B2, A1, A2, and these are maintenance technician. But with the new technology, we are now aiming to graduate. We call them technologists, and those technologists, they are not professional engineer, not 4 years, too much, but not also 2 years. And these are actually that's what we are aiming to do and to achieve. And we are successfully actually having 2 classrooms, and hopefully we'll start graduating the first batch of a student. And those students, they will be able to deal with the new technology, including hydrogen. Strala signed with Japanese company last month to do more work, and always Aviation Australia, we come to do the training. So we are going to train and graduate technologists who can deal with this technology, which is another important element we need to achieve. Now, this is Citralas, and as I said, Citralas, I really love them. They are very young, energetic guys, no PhD, no master, they don't need to do, they straight away jump to the aircraft and they start making the conversion. They are very, very successful. They've been in the business for almost 4 years. And now hopefully by 2030, they wanted to do the first clean sheet hydrogen electrical aircraft. And they want to push it to the market. They sign agreement. We all sign agreement with Qantas, Virgin, and Emirates, and so on and so forth. Some technical information, which I don't want to spend more time talking about it, but this is the target. and the sale, they aiming to have some sale of $1.3 billion by 2032. Then when this is for 9 to 19 Beech 1,900 aircraft, but within the time this will increase. These are the four boys who started the work, and they are actually the captain of this aircraft, and they are now progressing, and this number become 50. Because of that, we managed, this is Bob, managed to get a small aircraft from Perth. I think it's worth $1, he told me, and they start playing with this and converting this into hydrogen. Successfully being converted. One of the issue is producing liquid or liquefied hydrogen, but they've done it with the help of BOC, and now they have a nice cart full of bottles, and those bottles they're going to fuel the hydrogen. I think with this I will stop, and I will open the floor if there's any discussion, or we wait for the following speaker. Thank you very much, colleagues.
Okay. Thanks, Prof. Tala. Thanks, Prof. Tala. Okay, so we will open the Q&A sessions after our last speaker, Inji Jamali. Okay, so very quickly, Inji Jamali is graduated from Chemical Engineering Department, Widener University, and then he joined PETRONAS Research since 2001. He's actually a principal scientist in process technology. His expertise is in green-based oils, sustainable aviation, this SAF, low carbon syncrude production, biopolyesters, production of industrial applications, biowax, immersive coolings, and etc. Okay, so now Inji Jamali, here's your time. Okay, so yes, please. Thank you.
All right, Dr. Chin, thank you very much for the kind introduction. Hello, everyone. Good morning, good afternoon, good evening. So today I'll talk about the SAF. I'll go to basic. Thanks for the previous two speakers. I think what you guys shared actually is quite advanced. But for my turn, I go back to basic. Mostly about SAF. I can say like SAF 101, clear skies for tomorrow. So in this session, I'll talk about the high level of SAF and COSHA, which is a topic that is quite interesting for everyone because it represents complementary strategies for decarbonization in aviation industry. So before I talk further, so let me, this is the chemistry, the original jet fuel that coming out from refinery. As we know, the traditional fuel that fuel up our aviation actually coming from refinery, coming from crude oil. That's what we call kerosene, or sometimes we call it jet fuel in the range of 150 to 240 degrees C. For us that we mobilize across ground transportation, the one that we use most actually is the gasoline and diesel. In Petronas, we have Remax, our brand name, and then the diesel, the dynamic diesel, and also for base oil, actually also coming from crude oil, we have Etro. So as we moving towards sustainability, so of course we want to try to move away from the use of carbon. I mean from the fossil for fuel up our mobile, for our transport. So this is where the birth of SAF. So wait. So first, what is SAF? So SAF actually is a sustainable aviation fuel, which is alternative fuel made from a non-petroleum feedstock, in which based on our study, it can reduce up to 80% of the emission. And then it is a drop-in fuel because when we design the SAF, it should be compatible with the existing engine. So based on our pathways that we can blend, simply drop in with the fuel. So studies shown that we can blend up to 50%. And then at the moment, there are about 11 approved SAF pathways. There are two different versions. One is ASTM D7655, and another one is D1655. Later on, I'll show you the difference. So, and then what is CORSIA? CORSIA is it simply means a carbon offsetting and reduction scheme for international aviation fuel. So basically, it is to address our carbon neutral growth by from 2020. So imagine if we do not have SAF. So basically, it is anticipated that our emission will continue to grow because it is shown that aviation actually contribute about 2% of emission to the world. So this is where the CORSIA address how to address the emission. There are three approach. The first one actually is on the technological innovation. Basically, the better technology in terms of engine, better efficiency, and then operational improvement, basically to address the gap expected by the yellow shade here. This is mainly from the carbon traffic movement, something like that. And the remaining, actually, this is where we need to address by SAF, the one that fuel up the airline. Okay, so as we are moving towards sustainability, as I said earlier, we have transportation, we have ground transport and also the air transport. And then because for ground transport, we have electrification. So we expected the demand for gasoline may be a bit affected because of the rise trend of in the EV, electric vehicle. But for aviation, we expect it continue to grow. So this slide, this graph at below here show that the whole transportation industry actually collapsed during pandemic. But after the pandemic, especially on the airline, we anticipate it continue to grow. So we expect by 2025, this year or 2026, we should be able to recover to the level of what we achieved before pandemic. So the chart on the right basically tells about the projects in the world that try to do SAF across the globally. So you can see that Europe actually have the most number of projects. There are 58 projects over there. But in terms of capacity at the moment, US actually is still the biggest, about 24 million ton per year. And the chart below here actually is from the IATA regional workshop. It shows that the anticipated SAF capacity until 2030. We can see that from 2027, the capacity is a bit plateau because normally from FID until commercialization, it will take about 3-4 years. So at the moment, we have the data is only up to 2027. So we expect that with the more announced project coming in, the chart on the 28 onwards, we expected to rise. Okay, next, what is a sustainable aviation fuel, which is SAF? So mainly the feedstock for use of SAF actually coming from the waste feedstock. It can be coming from the plant waste. It can be coming from the used cooking oil, from the plastic waste, from domestic waste, even algae, and also industrial waste actually can be used as our feedstock. But if the material actually coming from the right side, for example, you require a lot of land space to produce your feedstock, that is not SAF. And then deforestation also is not a criteria for SAF. And also for the high use of water, also actually is not categorized as SAF. So the good thing of SAF, basically, the CO2 that we use basically is absorbed by plants and then produce a waste. And then this waste actually we convert into SAF. And then the SAF actually emits CO2. So over a lifetime, over a time, actually, this is the CO2 actually is we call neutral. So this is where we foresee that SAF actually can be sustainable over a long time. So in order for us to do SAF, there is a standard or systematic approach actually to evaluate whether it can be SAF or not. So according to ASTM D4054, this is actually the ASTM that we use to evaluate how the SAF actually is made. So there are 3 different test program. The first one actually is we call it the test program. There are 4 different tiers. The first one actually basically just to evaluate the critical properties of the SAF, whether it meet the typical jet fuel or not. And then for tier 2, fit for purpose, basically to beyond that specification, we need to see what is the impact to the possible impact to the engine. And then if it is okay, then you go to the next tier, which is the component or rig testing. And then finally on the tier 4, this is where we need to test on the actual engine. So in terms of volume, in terms of fuel volume, for tier 1, it can be as low as 10 gallon. But for tier 2, as you go to higher tier, the amount of fuel you require a lot more. Even for tier 4, it can be as high as 100,000 gallon, basically to test across the engine. Once you pass that program, you need to provide the report for OEM review. This is based on ASTM, and then from there, they will evaluate whether the one that you produce actually can meet into the existing ASTM, which is ASTM D7566 or ASTM D1655, or it maybe require some new process which we can be put under the new annex under this ASTM. And then after that, it will complete the process. So at the moment, there are 11 pathways. But over here, actually, I just show you on the 7 pathways under D7566. So basically, from the right, if you can see that the one that I talked about before actually is on the evaluation protocols, ASTM D4004. And then once you meet that criteria, you need to see whether it can be mapped against the existing STM here, D7566. If it is a really completely new process, it may be a new annex under this ASTM. And for the remaining, basically for D1655, basically to tackle for co-processing. Co-processing means whatever that you have can be simply blend into the existing jet fuel for use. But at the moment, for
Engineer Jamali, 5 minutes, yeah?
Okay.
Okay, yeah.
For co-processing, the amount that you can blend only up to 5%, but the remaining, it can be as high as 50%. Okay, so in general, this is a overall SAF processing route. And in summary, as I said earlier, our feedstock it has to come from the waste. It can be coming from used cooking oil, can be from the animal fats, or we call it tallow, or from the waste. So depending on the feedstock over here, actually it will dictate how the process actually it should be to making SAF. So in general, there are 3 categories. The first one actually is through the lipid conversion, which is the lipid coming from from UCO especially, and also the animal fat. So this is where we call the process actually we call HEFA. This is under A2. And then for biochemical, basically is to tackle for the organic waste, where you require to convert into sugar, and then you convert into alcohol, and finally into the jet fuel. So this is under the associated pathway is called ATJ, alcohol to jet under A5, and also for this one A3. Or sometimes we call SIP for sugar to synthetic isoparaffin. And the third category actually is a thermochemical conversion, Where typically this one actually require from the cellulose, even from algae and so in this category we require to convert into the syngas, and then we need to convert into hydrocarbon through a Fischer-Tropsch process. So for this one actually is under A1 in the ASTM method. So for jet fuel, this is a typical composition of jet fuel from the traditional process. So in order for you to make SAF, and that fuel is to be compatible with existing fuel, so you need to make sure that you have almost the same composition of that material. So you need to have paraffin. Ideally, you need to have all. You need to have a paraffin, isoparaffin, naphthalene, and also aromatic. Aromatic actually is still quite important in fuel. It's basically for the seal compatibility, for seal swelling. So then I'll talk about COSHA. So at the moment we are in the first phase of the implementation. So we are targeting by 2027, all participating countries actually will use COSHA, will use SAF basically to address the emission. Okay, at the moment there are 129 countries across the world already committed to participate in this initiative. So the last three countries that joining this year actually is from Comoros, Mauritania, and also Saint Lucia. This is somewhere at the Caribbean here, and also from Africa. So the one that from 2027 onwards, we should anticipate that most countries actually should participate and use SAF, particularly on the countries at green color and also the one in blue color, except the one in yellow. Okay, in order for you to make sure that the SAF actually is compatible, the right method actually to confirm its sustainability actually is through a life cycle analysis. So in general, whatever that you process, you need to calculate what is the LCA across the whole chain from the feedstock cultivation all the way until its fuel combustion, and you need to calculate what is the emission. So we need to benchmark with the normal jet fuel, which have about 89 CO2. So based on the approved pathways, these are the typical or maybe the default values for LCA. So once you have a new process, you need to validate this number based on the you need to compare with this default value with the actual number using the actual LCA method. So typically this one need to be verified with the third party, for example, with ISCC.
Inja Jamali can
Yeah.
summarize in 1 minute.
Okay, all right. Okay, so in 1 minute. Okay, across the world, basically these are the projects that already been announced, and they commit to produce SAF. My point over here, if you can see the color, most matured a pathway actually the HEFA, the A2. Even Petronas actually we are already have reached FID for make our biorefinery. So we target to be ready for commissioning in 2027, 2028. So hopefully Sunday later Petronas will mark our own HEFA at this map as well. Okay, in terms of this one is more on the estimated price based on the study because the process is quite complex, it's not straightforward. With based on the HEFA itself, the current price actually is about 4 times of jet fuel. So imagine if you have a more complicated process, it will complicate the process and make the process more expensive. So that's one of the challenge for HEFA, for SAF. So this is just what we are doing in Petronas, because in Malaysia we have a good what you call the feedstock in terms of palm oil. So we focus on this pathway. So even the one in biorefinery in Johor later on, we anchor on this approach. So in what we are doing in Petronas in R&D side, we try to enhance the one of the process under HEFA, which is we call the hydrodeoxygenation. So what we have demonstrated, basically we tested at the different scale. First we did in the lab, and then we did in the small rig using the catalyst 40 mil reactor, and then we further tested and validated at a much bigger catalyst reactor at 200 mil reactor, and the most recent one we already demonstrated at 1 liter reactor. So these are the pathway. These are the approach how we tested our catalyst and benchmark to the commercial one. So this is my last slide. This is all my team. We are coming from Fluid Technology Solutions. So we focus on fuels and lubricants. So SAF actually is one of the items that we're looking at. Okay, so thank you for listening. So over to you, Dr. Chin.
Okay, thank you. Thank you. Okay, so thanks very much for the three speakers. I think let me summarize what the three speakers share with us in this webinar. I think first of all, Prof. Shanian talked about the research strategy and the policy in UK on how UK government supporting SAF development in UK, and how UK can actually work with pull up different universities, government policies, and industry partners, for example Boeing, in shaping the research landscape in UK. Okay, so next, Prof. Tala. Prof. Tala mainly talking about how hydrogen can be used, and I think this is actually quite suit into the national strategy in Australia, because Australia producing quite a lot of hydrogens using different approach. And then I think one of the things that we can learn from, for example, Prof. Tala, is actually how startup companies can venture into this new business that never have somebody run it before, like for example a hydrogen fuel aircraft. One of the things that a little bit surprised me, Prof. Tala, is that when you present about an aircraft that with these fuel cells, I'm actually wondering, can the outlook, or maybe for example the shape of the future aircraft running on hydrogen fuel cell, can they have a different look from the conventional airplanes? Okay, and last but not least, from Inje Jamali, is actually what is the basic of SAF, and then the certifications of different for different pathways and things that is from the sharing of Inje Jamali. I have a feeling like the certification is always a challenge, especially for example for new technologies like SAF, that in this aviation industry that we emphasize quite a lot on safety, and now into this sustainability and things like this. Okay, so now first of all, I would like to say that let's have about 10 minutes of Q&A session. So first of all, is there any questions from the floor? Okay, so I think maybe for example, people still a little bit trying still to organize their thinking. Let me start the session. So to Prof. Shanian, I think one of the issue in actually, I think Prof. Tala mentioned it as well. One of the issue in the use of SAF, of course, other than the technology itself, is also what is the infrastructure need to be done in all the, or not, maybe not all, but big or major airports let's say for example in every country. And for example in London alone, that we have 3 or 4 major airports. And then, for example, in the north of UK, I think Sheffield is very near to Manchester, and people use Manchester airports almost quite frequently. So how the UK government supporting this approach? Okay, and then yeah, Prof. Shaniz.
Thank you. Yes, of course, as you know, SAF as an alternative fuel for aviation is very different than hydrogen as alternative fuel. If you use hydrogen, you need completely different infrastructure in airports, in transport, and all. So, but however, SAF is more of a normal conventional fuel. But what is important in UK is that, or how UK is dealing with it, is that there are many airports, for example, Heathrow Airport, Manchester, even other airports like Leeds, Bradford, or Bristol, Edinburgh, they are all involved on the SAF production activities. And therefore is really the airports also aligned with the fuel producers to make sure that where the fuel is produced still can use the same transport system to move the fuel about, and therefore minimum changes to infrastructure. I think that's the overall aim. What it means whether you send as a blend, because what we're talking about in here is the SAF, as you know, is only 10% by 2030. We still have that 90% of the aviation fuel will come from conventional fuel. So one of the issues that UK is now looking at is how do we decarbonize that 90%? We are all working on the 10%. We are doing a lot of things, but that will be only 10%. Can we also decarbonize the remaining 90%? And even with the best available targets, like European targets, that by 2050, 70% will be SAF, you still have 30% of the conventional fuel that you have to decarbonize. And therefore, we are now looking at LCAF. LCAF is the low carbon aviation fuel, how to change the structure of the aromatics. But once you do that, you have a problem with the, as our previous speaker said, issue with the certification. And therefore, one of the biggest challenge is the certification, especially as you showed before, there were many different routes of the SAF production. And how do you certify those type of fuels? Are they within what is available at this moment through ASTM? And therefore, these are the challenges. But I think airport, in terms of infrastructure, providing this blend fuel is available, or blending capabilities are available, there is not much in infrastructure needed within the airports.
Okay, thanks. Okay, Prof. Tala. So how do you think about, with the, let's say, for example, for the hydrogen fuel cells, I think the I think the layout, or maybe, for example, the future, it will change the future look of planes, that rather than conventional than what we see. What do you think about it?
Yeah, no, look, this been considered by Citralis, and I am happy to share with you. You can see, right? This is they called it clean sheet hydrogen electrical aircraft. This is the new shape which they aim to have, because basically they remove the gas turbine from here, from the wing, and now they push the fuel cell at the back. So you can see the whole aerodynamic now need to be considered. And I'm talking about the beach, the small size aircrafts. While if you look at the old one, and you can see now, this is the gas turbine, right?
Yeah.
And that's why you can see a lot of differences. I'm sure, the team can talk more and more in than what I say, because for me, I look at the bigger picture. I see them from time to time. I'm not
Yeah.
heavily involved in the technical conversion, but
Yeah.
I would say I'm very impressed. So that's basically the new shape, and you are very right. Actually, that's why they call it clean sheet. So it will be one sheet, and that's it. Just regarding what Professor Shenin said, I totally agree. Actually, one of the main challenges is the regulator, because now you can do anything you want, but still, if CASA or EASA they're not cooperative, it's very difficult. Even with Malaysia, I think last year or beginning of this year, I visited CAA M, and they asked the same question that we received from our CASA here. So and agree, infrastructure of SAF is less complicated than ours. But in Brisbane now we have gas station pump hydrogen, just for your information. I have some photo, but it's too late for me to show you. Thank you.
Okay, thanks. So, Engineer Jamali, also a very quick one. Certification seems like it's an issue, but how do you think this can actually, for example, impact to the business opportunities and things like this?
Yeah, because we need to go through the third party, the appointed one. From what I know is we need to go through the ISCC. So what happened is we need to during that certification, you will certify even, for example, the feedstock. When we import the feedstock, for example, the used cooking oil, let's say we collect, we import from somewhere else. That UCO also need to have a certification.
Mm.
And
Mm.
then for each of the stage gate, for example, in our HEFA process, we have a pretreatment, we have a hydrodeoxygenation. So of each process, we'll need to go through, we need to evaluate what is the emission. So basically, based on the mass balance, we need to see what is the CO2, the CFA. So along the way, so at the end, what is the emission? So I guess
Okay.
the challenge, how to make the process as low in terms of emission as low as possible, because every time you introduce new, for example, you in terms of logistic, for example, you import from further away from your location. Actually, the amount of fuel actually will impact that certification in terms of the emission.
Okay. So, Prof. Shanian?
Yes, just to clarify in terms of certification, you have two types of certification. One is for the environmental certification, sustainability, which is ICAO and other organizations looks at it as a part of whether they receive funding or whether they receive subsidy if their low carbon technology is being used. But the important challenge is the ASTM certification, which has nothing to do with emission, is mainly on how safe this fuel is to be used at international level. And that is the very challenging one because they have a different route already approved, 8 different routes, 9 being investigated, and it's a very long process. You have to go through pre-screening, tier 1, tier 2, tier 3, tier 4, and very expensive process. So that is the biggest challenge, and to make sure that all these new fuel producers are aware of this long process. And that is what I mentioned about SAF clearinghouse, which at the moment only the US, but now UK is doing it, and the European Union is also looking at it.
Okay. Thank you. May I know any question from the floor? Any question from the floor? Please do not shy if you have any question. Okay. In that case, Any? Oh, okay, so in that case, what we will do is that can I request our speakers just very quickly, 1 minute, draw a very quick and solid conclusion on your talk and what is your view? Just very quick, okay? Okay. Shall we start from this time? Can we start from Inje Jamali? Is that okay?
Yeah. I mean the summary, yeah.
Yeah, just a very quick one.
Yeah, okay. We see, for me, I see that SAF actually is a good potential, but in terms of commercialization, there is still a long way. It's still not finalized yet because everyone actually looking into how to make SAF the most affordable, because everything actually is back to economic. If you come up with something new, you can produce SAF, but if it is not economical, basically you cannot go. So that's one of the challenge for in the fuel industry, especially actually in the aviation industry as well. So even for now, for the established pathways, we're not sure how the price transfer into the customer, because it's still under pilot phase, right? So by 2027 onwards, of course, there is the plan actually is there is carbon trading, but we're still not sure how the price is translated into the consumer in terms of ticket price. So that's something that we are looking for and looking forward at all.
Okay. Okay. Thank you. Thank you, Inje Jamali. Prof. Shanian, very quickly.
Yes, just to conclude for today is really possibly I have to mention that decarbonization of aviation is an international challenge. And one of the areas that we really need to look at by being an international challenge, international collaboration is very important. Learning from each other is very important. When aircrafts are flying around, they don't consider the borders, they fly all over. So the emission generated, the countries that generated covers not only certain countries, but everywhere. The biggest challenge is how to make sure that the private investors, because don't forget government can't do everything, it's the private investors that has to have a confidence in order to get into the market, in order to produce fuels. And to do that, politicians have to provide that certainty that government change will not change the policy. There is a subsidy to kickstart the work. And once that certainty is there, then private investors will take over. Once private investors take over, the pricing will not be an issue because the market will decide on how to deal with pricing. And you can sort of look at the previous examples. For example, NOx emission back in 1980s, to reduce the NOx emission in combustion process was very expensive process. Now it's a very common and very cheap process that big companies do in every process. So let market take over and do it. But more importantly, don't rely on HEFA, rely on the next generation technology where life cycle analysis shows 99% reduction on carbon footprint. And that is very important. So academic research to provide that next generation technology is essential, followed by of course, international collaboration.
Okay. Okay. Prof. Tala?
Yeah. I echo what Professor Shanian said. Work together. Don't recycle as well. If if Germany can produce the best electrolyzer, don't waste your time by producing another electrolyzer to fight with them. Complement what they are doing, and that is something I really encourage all my colleagues, staff, and students to do that. The price of green hydrogen is still expensive. We need again to reduce it. That's one of the hopefully the question I throw always to the table, and hopefully someone can continue investigating while we're waiting for CASA, EASA approval, you know, because this is going to be a very lengthy process. Last technical question. I just want all of us to imagine there will be thousands of aircraft flying 10,000 meters above sea level, all emitted water. How is the environment going to look like? We need to imagine, and this actually question needs some really answer. And I'm not saying it's always positive. I don't know. Thank you very much.
Okay, thank you. So thanks everyone for your attendance. Thank you for the speakers who give us insights into the SAF development of SAF from different regions. So thanks very much. Before we conclude the session, I think it's okay. Is it okay that we take a photo? So for the attendees, if you want, you can open your camera. So for the speakers, just we take photos together. So please. Okay. So 1, 2, go. Okay. Thank you. Thank you very much. Okay. So again, thanks everyone for your time. Okay. Thank you. Thanks. Thank you.
Bye.
Thank
Bye.
you.
Thank you.
Thank you.
Bye.
Have a lovely night.
Bye.
Bye.
Thank you for the meeting.
Bye. Yeah.
Bye.